We're looking at a paper that just dropped called First Proof. It's from February 6th, 2026, and the author list is a massive collaboration. We're talking mathematicians from Stanford, Columbia, EPFL, Yale, Berkeley.
And the headline here is that we've basically hit a wall. For the past few years, it's been all about AI models just crushing Math Olympiad questions. They win gold medals.
Right.
But the authors of this paper, I mean, you see names like Abuzaid, Harrer, Spielman. They're arguing that those benchmarks are totally artificial. They measure how well you do in a contest, not whether you can actually do research.
So their solution is, I think, just fascinating. They've released 10 research-level questions pulled directly from their own unpublished work.
And this is the key.
We're talking about fields like algebraic combinatorics, spectral graph theory, symplectic geometry. This is the absolute frontier.
And here's the mechanism that changes everything. The answers are known, but only to the authors. They're encrypted and sitting on a website right now, firsttproof.org, and because they're not on the internet...
Zero data contamination.
Zero.
So what were the initial results? They ran this against GPT 5.2 Pro and Gemini 3.0 DeepSync.
And the verdict is pretty stark. In a one-shot setting, these state-of-the-art models, they struggle. They basically fail.
Which just highlights this huge gap between, say, solving a homework problem, even a really hard one, and doing the actual work of a research mathematician.
It's effectively drawing a line in the sand between calculation and genuine creation.
Okay, let's unpack this. That was the snapshot, but I really want to get into the philosophy here because the title itself, First Proof, that's not just a random name. It's a very specific metaphor, right?
It is, yeah. It's actually a baking reference. In bread making, the first proof is the bulk fermentation. It's that stage where you let the whole massive dough just sit and ferment before you shape it.
Okay.
And the authors are using that to describe these problems. They're still fermenting. They're the raw, kind of messy ideas that eventually become polished theorems.
I love that image. It really pushes back on this idea of math being just input question, output answer.
Exactly.
But it also gets at the distinction they're making between contest math and research math. And I think for a lot of people listening, even ML engineers, that distinction can feel a bit blurry. I mean, if an AI wins a gold medal at the IMO, shouldn't it be able to write a research paper?
That's the common misconception, yeah. Contest math is all about finding a very clever trick to solve a perfectly defined problem in a few hours. Research is an expedition. The authors bring up the Poincaré conjecture.
Right, Perelman's proof from the early 2000s.
Exactly. Perelman crossed the finish line. But the really hard part of that research wasn't just his final sprint. It was all the years of work by people like Thurston, who developed the frameworks for geometric objects, and Hamilton, who invented Ricci flow dynamics.
So most of the work is building the world in which the proof can even exist.
Yes. And this paper is very clear about its scope. They're not asking the AI to, invent a new theory of everything or replicate what Hamilton did over decades.
So what are they testing?
They're focusing on that final stage of research, proving a well-formed statement where all the definitions and the frameworks are already understood. It's a test of pure technical execution at the frontier. They're basically saying, here's the setup, here's the destination, can you build the bridge?
Which brings us to the design of this whole benchmark. You mentioned data contamination. That is the elephant in the room for every single AI benchmark.
It's the #1 failure mode of evaluation. If the answer is on the internet, the model has trained on it. It's that simple.
So the first proof strategy is to use questions that are completely fresh.
Right. They're extracted from lemmas like intermediate steps in and larger papers that are still in progress. They haven't been published anywhere.
So the AI literally cannot have seen the answer.
It can't. And they put constraints on it, too. The proofs are all roughly 5 pages or less.
So that's to cater to the context window of current models.
Exactly. These aren't problems that would win a Fields Medal on their own. They're the sort of heavy lifting components inside a future publication.
And the answers are encrypted until February 13th, 2026. So there's a ticking clock. I also noticed they insist on human grading. Why not just use formal verification languages like Lean?
You could, but translating a research problem into a formal language is a massive research project in itself. And, unlike a contest where the answer is just a number, a research proof can have multiple valid approaches. Or maybe the model finds a counterexample nobody thought of. You need an actual expert to read the output and say, yeah, okay, this logic holds up.
All right, let's get into the meat of it, the 10 questions. This is what makes the paper so impressive. It just spans so many different fields. I think we should walk through a few just to give people a sense of the actual ask.
It really is a tour of modern mathematics.
Okay, let's start with analysis. Question 1. It's about a 3D unit torus and something called the 543-3 Mera measure.
Right, this is deep in stochastic analysis. The basic idea is you have a measure, call it a $, and then you have a shift map defined by some smooth function. The question is pretty simple to state. Are the original measure and its shifted version equivalent?
And when you say equivalent in measure theory, that doesn't just mean they're equal.
Correct. It means they agree on what's impossible. So sets that have 0 probability in one measure also have 0 probability in the other. Proving this means you have to handle infinite dimensional spaces. You can't just bluff your way through it.
Okay, jumping around a bit. Question 4 is also analysis heavy, but it's about polynomials. This one defines this weird convolution operation, box plus again.
Yeah, this is a classic inequality problem. You have to prove or disprove a relationship involving this function infimity, which is a sum of squared inverse differences of the polynomial's roots.
And the trick is that this convolution operation, box plus alone, isn't standard.
It's not. The authors defined it for this problem. So the AI can't just look up its properties. It has to derive them from scratch and then apply them to a really complex inequality. It's a test of pure adaptability.
Let's switch gears to the more structural stuff, like geometry and topology. Question 8 on symplectic geometry feels very visual. It's about polyhedral Lagrangian surfaces in MathPR.
It's super geometric. The setup is you have a surface made of flat polygons, and at every corner, exactly 4 faces meet. The question is, can you always smooth it out?
Meaning, can you get rid of the sharp edges without breaking the underlying physics of the space?
That's a great way to put it. It's called a Lagrangian smoothing.
Yeah.
You're checking for rigidity versus flexibility. Is the shape fundamentally stuck being sharp, or can it relax? And doing that requires a kind of spatial intuition in 4 dimensions, which is notoriously hard for LLMs.
Question 7 is in that same world, topology and group theory.
Yeah, this one's a mouthful. It asks about uniform lattices in real semi-simple groups. Can a structure like that be the fundamental group of a specific type of compact manifold?
So it's about connecting a very abstract algebraic structure to a physical shape.
Exactly. It's asking if this algebraic object can actually exist as the blueprint for a certain kind of space.
Okay, now let's talk about the questions that feel more like reverse engineering. Question 3, in algebraic combinatorics, really stood out. It's about Markov chains.
Yes. Usually with Markov chains, you're given the rules and you have to find the final stationary distribution.
Right.
Here, they do the opposite. They give you the distribution. It's this crazy product of 2 very complex types of polynomials, and they ask you to construct the Markov chain that produces it. And it has to be non-trivial.
So you can't just say the chain that stays put.
No, you have to actually build the transition rules, the mechanism that results in that distribution. It's a design problem, not a calculation problem.
And then there's the really applied stuff. Question 6 in spectral graph theory.
This one has huge practical implications. It's about graph Laplacians. They define something called an epsilon light subset. And the question is about existence. Does a constant exist so that every graph has a reasonably large epsilon light subset?
Which would be massive for algorithms that break down big networks.
Huge.
But the boss fight for me, in terms of real-world constraints, has to be question 10. Numerical linear algebra.
Oh, I agree. This is the most practical of all of them. It's about tensor decomposition with missing data.
And the constraint is just brutal. You have to explain how to use a specific type of iterative solver.
And this is the key. You have to provide a complexity analysis that avoids dollar and computations. Where n is the total size of the tensor, you have to use the fact that the data is sparse.
So it's not just solve it, it's solve it efficiently on a real computer with real constraints.
Precisely. An AI might give you a theoretically correct algorithm that would take the age of the universe to run. This question forces it to understand computational cost.
So that's the gauntlet. 10 problems, 10 different mathematical languages. So what happened when they tested this? The paper says preliminary tests with GPT 5.2 Pro and Gemini 3.0 DeepThink.
And the verdict was pretty blunt. They struggle to answer.
What does struggle even look like? Is it just making things up?
It's a mix. In that one-shot setting, they just fail to build the logical chain. They might understand the definitions, but constructing a 5-page proof without, getting lost or assuming something that isn't true, it's just beyond them right now.
But the authors do say that iterative interaction could help.
Oh, for sure. If a human expert was there to guide it, saying, no, that's a dead end, or you made a mistake on line 3, the models might get there. But they stuck to a strict one-shot protocol to establish a clean baseline.
We should put this in context. How does first proof stack up against the other benchmarks out there, like frontier math or real math?
It's in this really interesting sweet spot. So you've got frontier math, which is OpenAI funded. The problems are private, which is good, but the answers are just numbers or symbols. So it's auto-gradable, which is great for RL, but it doesn't test proof writing.
Right, getting the answer 5 is not the same as explaining why it's 5.
Exactly. Then you have things like real math, which scrapes R5. So the questions are public.
But potentially contaminated as soon as they're posted.
Right. First proof kind of gets the best of all worlds. The questions are from the true distribution of what mathematicians actually work on. The answers are totally unpublished, so zero contamination. And the questions themselves are public, so the whole community can inspect the test.
And they allow full internet access during the test.
Which is so key. Real mathematicians use Google. They look up definitions. A benchmark that locks an AI in a vacuum isn't realistic.
It really does feel like a reality check. It's moving the goalposts from can you win a game to can you contribute to a paper.
And that's a monumental shift. The authors are very clear. Current AI is great for literature. The core creative act of generating the new part of a proof, that's the frontier.
The paper ends by looking ahead. They're planning a second set of questions, maybe without that 5-page length constraint. I mean, imagine asking an AI for a 20-page proof.
That's a whole different beast. Managing logical consistency over that length is a completely different challenge.
So here's the thought I want to leave everyone with. The paper touches on this. If AI eventually does solve these questions, if GPT-6 just breezes through that symplectic geometry problem, does that mean the AI is creative?
That's the billion-dollar question. It's the classic AI effect, right? As soon as a machine can do something, we just relabel it as mere calculation. But if it's performing that bulk fermentation, connecting ideas to form a new proof, we might have to admit creativity isn't exclusively human.
Or, as the paper sort of hints, maybe we humans just move further up the stack.
Right. We focus only on what is the right question to ask, and the AI handles the how do we prove it.
The what becomes the only job left.
Yeah.
Well, if you want to see if you're smarter than a 2026 AI model, or if you just want to stare into the abyss of spectral graph theory, you can go check out firsttproof.org.
Good luck with that. You probably need it.
Thanks for tuning in. We'll see you on the next one.